All right. Hi, everyone. I'm John Rice. I'm a research assistant professor here at the university in the Department of Biostatistics and Informatics. And I'm going to be leading this breakout session today on correlated data and talking about basics of linear mixed effects modeling. So throughout, I think the moderator will be looking at the chat, and if you have questions, please feel free to leave them in the chat, and she'll let me know, and I can address them because I'm hoping this will be as interactive as we can make it. So first, what is correlated data? So correlation arises when either pairs or clusters that are larger than pairs of observations are related and therefore more similar to each other than they are to observations outside of that cluster. So this can arise in a number of ways. This could be repeated measures on an individual person, so a patient kind of observed over time. It can be observations of different items on the same subject. So this often comes up in certain kinds of studies where you're looking at, for example, left versus right eyes. So this is a case of one might serve as a control and the other is exposed to some sort of treatment. Families are another example of clustering because you expect certain traits to be more similar within families than between families. And patients from the same practice or hospital or clinic or provider. And that's another way clustering can occur is there's hierarchical clustering. So there could be patients that are clustered within a provider, within a practice. So there's a lot of ways that this can come up. So why do we use clustered data? So there's a lot of reasons for use of clustered data and some kind of disadvantages as well. But there's often the case, especially in pragmatic research, that for logistical reasons we can't randomize at the patient level, and this is often due to the fact that the intervention being tested is it can only be delivered at a cluster level. For example, it can only be delivered at the county level, depending on certain kinds of interventions. So in many cases you can't randomize individually. Ethical issues that could come up. For example, this happens, for example, when there's an intervention that kind of is expected to be quite beneficial, and you are going to be you might have difficulty recruiting practices or clinics to participate if they fear that they will be randomized to control. So in that case, a stepped wedge can be a very advantageous design because in that design, each cluster eventually receives the treatment. The randomization part is the order in which that happens. So another, if certain research questions are only able to be answered using cluster data. So if we're looking at the effect of an intervention over time on the same patients, then this would be something that we would need to account for clustering within patients on to really gain the benefits of that kind of design, because that will take advantage of the within cluster correlation I'll talk about in a moment. And then finally, generalizability. So clustered data often allows you to include data from multiple sites to obtain a more diverse patient population and potentially a larger sample size. So how do we measure clustering? So typically this is done using something called the interclass correlation coefficient, or ICC. And if anyone's familiar with the Pearson correlation coefficient, it's similar to that. It's just used to measure the interrelatedness of observations within a cluster instead of kind of the pairwise correlation that the Pearson correlation measures. So if we think about it as partitioning total variability into two components within cluster variance and between cluster variance, then the ICC is equal to the between cluster variance divided by the total variability. So it's the proportion of variability, of total variability, that's explained by the between cluster variance. So in terms of design matters or design questions, as the ICC increases, you're going to need more clusters and more patients in a cluster randomized design. And it's always going to be more efficient to increase the number of clusters than it is going to be to increase the number of patients within a cluster. Because essentially, your clusters are your independent units in a cluster randomized trial. So, increasing the size of each of those independent units is less impactful than increasing the number of independent units. So when we're planning studies, it's often kind of unclear what number to use for ICC. Sometimes there's preliminary data or previous studies to suggest what this could be, but we often assume something in the range of zero point zero 0.01 to zero point zero 0.05. So a few examples of clustered designs. This is kind of the typical, top left here is kind of the typical cluster randomized study, just parallel arms. So if you can think of, the x-axis on each of these as time, and then the y-axis is, or the rows or clusters, each of these clusters stays for the full period of the study in the same arm. So the dark blue is the intervention arm, and the light blue is the control arm. So that's kind of the basic cluster randomized design. Then we have introducing a baseline period. So both arms start out in control, and then randomly one set of clusters transitions to treatment. And then so this would be something like a difference in differences type analysis, potentially, where we're looking at the difference in change over time between the arms that are randomized to treatment and the arms that are randomized to control, or the clusters that are randomized to treatment and control, sorry. And then here's the stepped wedge design that I mentioned a moment ago. So in this case, the clusters each start in control, but then in random order and sequentially they cross over into intervention. So by the end of the study, all of them have received the intervention. This is why it's often, advantageous to use this design, because you need to get buy-in from each of these clusters. And if they all know that they're going to eventually receive the intervention, they're going to be potentially more willing to participate in your study. And then finally, there's kind of a variation on the stepped wedge that includes a transition period, because it's often, you don't necessarily want to use the data during the implementation of your intervention, because you wouldn't expect that you would have kind of full effectiveness immediately. So you often introduce this transition period where data is not, it may be collected, but it won't be used for analysis. So cluster designs are going to be more complicated to analyze and to actually work with generally than independently randomized designs. So again, one limitation is going to be the number of clusters that are available, and this is why the participation is so important. You need to get these clusters to buy in. As I mentioned before, with a larger ICC or more interrelatedness within clusters, you're going to need an increasingly large sample size, because you're getting, it's getting closer to the idea of each cluster, is an individual unit. And again, for an individually randomized trial, you essentially need to inflate your individually randomized trial sample size by a variance inflation factor that involves this ICC. So it's in that sense it's maybe less efficient than an individually randomized trial. But as we saw before, there are a number of logistical reasons where this is kind of the design that you might need to use. So, in terms of analysis, it's really important to take into account clustering. As I said, it's more complex to do so, but if you ignore clustering, then you will often end up with misleading inference. For example, your standard errors can be too small, which may lead to inflated type 1 error rates, or false findings of significant effects. So another kind of correlated data that arises is repeated measures. So this is a little bit different. So when I was talking about cluster randomized designs, that's more like, we have practices or clinics or hospitals that are randomized to one of two arms or potentially more arms. But correlated data also arises in this repeated measures context. So each cluster then is kind of observed over time for sometimes. And so this is another way to think of correlated data, or another way correlated data can arise. So repeated measures can also occur across levels of a controlled factor. So this would be something like in a crossover study, when subjects each receive multiple treatments. This can be as few as two, or it could be more, sequentially with washout periods in between. So this is kind of this can be an efficient design because again you're taking advantage of within subject correlations, and often you would want to randomize the order in which they receive these treatments. And then longitudinal data is data collected over time on a sample of units, which could be individuals or other units. So, for example, subjects with torn ACLs assigned to one of two surgical repair methods and then followed through time. So you'd obtain up to four measurements on each of these subjects at each of these time points. Um, and then this would be contrasted with cross-sectional data where you're only looking at individual patients or people or units at a certain point in time. So there can be some advantages to this, as I've been alluding to. There's power advantages sometimes in using those within cluster differences or changes, but there's certain things that can just only be looked at longitudinally. That's the only longitudinal data is going to give you that information on individual patterns of change as compared with cross-sectional studies of different patients at different times. That's not going to give you the same level of information as following the same people over time. And it can be, kind of the flip side of the power thing I'm talking about is you need fewer subjects for the same level of power. Because in longitudinal studies, each subject can serve as his or her own control, essentially, if you're comparing treatment effects. So that could be something like a crossover design. And the power gains or the sample size economization occurs because you're making comparisons within a subject rather than between subjects. And this is kind of the one of the key points of correlated data is what happens with it depends on whether your comparisons are between clusters or within clusters. So between clusters is when you have cluster randomized data. Within clusters would be something like where you're exposing the same individuals to different treatments over time, for example. So some disadvantages, primarily, I think, other than the power loss that you can run into with cluster randomized designs, these are going to be more complicated analyses statistically. And there's many different ways to analyze cluster data. We're going to talk about mixed modeling today, but there are certainly alternative methods to analyze correlated data, and they lead to different interpretations. So it's not always straightforward to know what is the best method for analysis in a correlated data study. And again, your interpretations are going to depend to a certain extent on the methods you choose. Um, so another issue is kind of unbalanced or missing data. And again, most modern statistical methods account for this pretty well, but it is something that doesn't arise in studies without clustered data because there's no notion of something like missed appointments. You just have a single observation on each person. And again, in some types of cluster data, the cluster sizes may vary, and this, of course, occurs with families with varying family size. Things like if hospitals are your unit of randomization, they obviously will have different numbers of patients, and that can cause complications with again some of the older, more basic methods of analysis. As I said, kind of interpretation can be difficult because there are multiple methods for analyzing this kind of data. And depending on what you're doing, methods may not actually, exist for some of these problems. So you may have to go a little bit outside the box sometimes when you're analyzing clustered data. So simple example here, scenario is two normally distributed measurements taken at two equally spaced visits. So first visit is serum cholesterol on a standard American diet. Second visit is serum cholesterol measurements on the vegetarian diet 1 month later. As I mentioned, this is maybe not the best design for this because ideally, or often you would want to randomize the order in which these treatments occurred. So you could remove that kind of source of possible confounding from your analysis. But this is the design we're talking about here. So there's a few different things you can do as kind of simple longitudinal analyses. You can look at the change score as your outcome. So that's where you take the difference from pre to post. And you can analyze that in a simple linear model with just an intercept. Because the linear intercept is your within subjects mean change from pre to post. So this would be kind of the mean value of someone's cholesterol on the vegetarian diet minus the mean value on the standard American diet. And then we would be testing the null hypothesis that that change is equal to 0. And this would be equivalent to a paired t-test, essentially. Getting a little bit more complicated, but still in the linear regression framework, would be including the baseline as a covariate. So here your outcome would be the measurement at time 2, and the covariate would be the measurement at the time 1. So you'd fit a linear regression model now with an intercept, but also with this covariate y0. So then you could test the null hypothesis that the mean post-cholesterol is not associated with pre-cholesterol levels. So it's a little bit different question here. And then finally, we have a hybrid model, which is the change is the outcome, but adjusting for baseline. And in this case, it's a linear regression model for that change score, but with an intercept and then a covariate for the baseline measurement. And in this case, the slope, or gamma 1, indicates whether the change in cholesterol is related to the baseline value. So it's different questions with each of these, but each of these are kind of simple methods for analyzing longitudinal data.
Hey, John, just
So
wanted to give you a quick time check.
yes, thank you for that. Yes, thank you. So now linear mixed models, kind of focus of the talk here. This is generally a better method for analyzing longitudinal or clustered data than the methods I was just describing. So these typically assume that the outcome is continuous and approximately normally distributed. This is usually, not the case. You often have variables that are potentially very non-normally distributed that you can still analyze in this framework as long as certain other assumptions are met and you make certain adjustments to your methods accordingly. Because really the key assumption is that the residuals are actually normally distributed. And that's something you can check with diagnostic measures. So again, these are methods that are useful for repeated measures, longitudinal and clustered data. And then if your outcome's not approximately normal, you can consider things like transforming the outcome. So log transformations are often seen here. But there are other transformations as well, depending on kind of what your data looks like. And when you transform the data, you can then typically apply linear mixed model methodology as you normally would. The issue then becomes interpretation. You can end up having kind of a more complicated interpretation if you've done some strange transformation to your outcome. And then there's other options such as mixture distributions or non-normal outcome models, because those exist as well for cluster data and are actually at this point quite well developed. So that's if you have binary data or count data, time to event data, things like that. So the key feature of a mixed model is that it has both fixed effects, which are the regression parameters that we're used to seeing, and random effects, which are kind of subject level regression coefficients. So in the mixed modeling framework, we estimate these regression coefficients or the fixed effects directly. And the random effects, we only estimate their variance or their covariance parameters. So essentially, mixed models allow for a more complicated error covariance structure, which allows you to model that dependency within clusters. So just some quick notation here, just to point out some things. The linear mixed model is defined this way. So we have our outcome here on the left-hand side, and then we have our contribution from our fixed effects here, x beta, plus a contribution from our random effects, zb, and then our residual error. And kind of the zb part is what makes it a mixed model, essentially. Although we can also specify correlated data analyses by treating epsilon differently. But the ZB part is the random effects part of the model. So just to point out some comparisons, differences, and similarities between mixed models and kind of classical linear regression methods. Um, it's a similar framework. So the regression coefficients are going to have similar interpretations. So for example, a slope or a covariate effect will be the expected change in the outcome associated with a 1 unit increase in the value of the covariate. That's still going to be essentially the same interpretation with a mixed model. Estimation methods are going to be similar. We're going to be using maximum likelihood in the mixed effects framework, possibly something like restricted or residual maximum likelihood, which is kind of a small sample adjustment to maximum likelihood that gives you, um, in theory, it gives you less biased covariance parameter estimates for small samples. And then testing and inference is often based on the same, t statistics. So the ratio of the beta hat to its standard error. What's different or what's new is that you need to additionally specify the correlation structure of your data. And you can do that either directly. So this would be a covariance pattern model where you specify structures for that epsilon, that vector in the equation on the previous slide, or indirectly through a kind of random effects model. And that's specifying that ZB term in the equation on the previous slide. Um, so covariance pattern models are going to be working directly on the correlation structure for the outcome. And these, I'll talk a bit more about some specific examples. But those work directly on the outcomes correlation. But random effects models are going to specify a set of random coefficients, which includes random intercepts and random slopes. And then we're estimating their covariance matrix as part of our model fitting procedure. Um, but specifying a model this way is going to lead to correlation in the outcomes within a cluster kind of indirectly. So these are the two paradigms. You can kind of specify your covariance directly through a covariance pattern model or indirectly through a random effects model. So these covariance pattern models are going to have the same kind of estimation methods. Again, we're looking at maximum likelihood or restricted maximum likelihood typically, but what you're specifying is different. So there's a lot of options here, but a lot of them depend on certain data structures. For example, a lot of them are kind of based around measurements taken over time. And that would be something like the AR1 or autoregressive of order 1, which leads to decreasing correlation with increasing separation in time between observations. And this is often a pretty good approximation for correlation structures and observations that are taken over time. Compound symmetry is kind of the simplest option, and this is actually equivalent to a random intercept model, which we'll talk about in a moment. And then there's a few other kind of options here. Toplets allows a different covariance for each pair of observations that are separated by the same number of time units. So it's a little bit more general than something like AR1. And then finally, there's an unstructured option, which for all but kind of the simplest situations is going to be probably untenable, but it is the most flexible option. So it can give you a better fit to your data. So random effects models can be kind of thought of as random intercept models and then random slope models. So the special case is kind of the random intercept model. So that's just adding a single random effect to the model, which is basically a single random value for each cluster that you then estimate the variance of those across clusters. And this is, not going to necessarily address issues of correlation over time. But for example, if we're looking at a cluster randomized study, you wouldn't expect really different members of the cluster to be differently correlated with each other. You'd expect them to kind of have the same level of correlation with any other member of the cluster. And this is going to be another way to account for this between subject variability, and induces a certain, as I said, it's equivalent to the compound symmetry correlation structure. So it causes it gives you the same correlation between any two members of your cluster. And this is often too simple for some data taken over time, because I mentioned there's some other options there like AR1 and some others as well. But is almost always better than ignoring correlation. Random slope models are kind of a generalization of the random intercept model, where you're now not just including a random intercept, you're allowing population heterogeneity also in the effect of covariates on the mean outcome. For example, if you have a random slope for time, this will allow for changes in the variance and covariance over time. So for example, one thing you might see with clustered or with longitudinal data is that the variance will increase over time. And this is something that you can model with random intercept and random slope for time. Um, so one thing to make sure of, though, is that any covariates that appear in your model with a random slope have to vary within clusters. Otherwise, you can't estimate them. So again, time will vary within a cluster when you're taking measurements over time. But something like race or ethnicity would typically not vary over time. So that would typically not be, estimable within an individually randomized study when you're taking measurements over time. However, if your clusters are not individuals, but something larger like a medical practice or a hospital, you could maybe estimate a random slope for something like race or ethnicity. It all depends on kind of the context and the source of the data. So another thing to keep in mind is as with that unstructured covariance pattern model, each random slope is going to add to your total number of parameters that you need to estimate in this modeling framework, because you have both the variance for the slope itself, and then typically you need to estimate a covariance between that slope and all the other random coefficients in your model. So it's unusual to see models with more than one or maybe two random slopes. And again, you need to think about the kind of the interpretation that you're attaching to these models when you take this kind of approach, because the random coefficients modeling approach is going to give you kind of different correlation structures that are not necessarily easy to predict what they'll look like in comparison to the covariance pattern modeling approach. So kind of to sum up here, mixed models are a way to analyze continuous, approximately normally distributed data when there is correlation between units within some clusters. And it can provide additional efficiency in some instances. For example, a paired t-test is going to require observations on pre and post on everyone. But a mixed model, which is equivalent to the paired t-test under certain assumptions, it will still work even if some subjects are missing data at one or the other time point. So they can take advantage of all your data rather than having to kind of exclude people with missing data or exclude clusters with missing data. And mixed models typically will be accounting correctly for the effect of correlation on inference. And this can also impact the estimation of regression parameters, and this will be something we'll see in the example, which we'll have to go through pretty quickly, but we'll see that there. And then, standard errors are typically going to be over or underestimated in naive analyses. So, for example, between cluster comparisons are going to typically have their standard errors underestimated, while within cluster comparisons will typically have their standard errors overestimated in naive analyses. So I'm going to stop there and pause for questions while I get the example up here.
I haven't seen any in the chat yet, so
Okay, thank you.
feel free to put in the chat.
Just got to find the right screen here. Okay, can everybody see the example here with some code and some output?
Yes.
Okay. So again, we'll go through this quickly, but this is a simulated data example of a mixed modeling situation. So this is where we have an outcome that is test score and a predictor that is weight, and we want to examine the relationship between this covariate or this predictor and this outcome. But we've collected this data from a set of 8 clinics, each of which has 3 different providers associated with it. So kind of looking at a summary of the data, our test scores range from 0 to 100, our weights range from 162 to 236, and then we have 60 observations associated with each of these 8 clinics, and a certain number with each provider within clinic. So again, these providers are lettered A, B, and C, but they're not meant to indicate the same provider. It's just that's they're not the same provider across practices or across clinics. It's just the naming scheme. So one of the first things we always like to do is to look at the distribution of our data, and this is again the marginal distribution because this is not dependent on, we haven't accounted for any variability associated with weight, but marginally at least our test score data looks reasonably normally distributed, which is a good thing. So kind of the first step we might want to take is to analyze the data assuming independence. So in this case, we get a significant effect for the effect of weight on test score, which is kind of contrary to what we expected, given our initial hypothesis. And if you look at the scatter plot, you can kind of see where this is coming from. So we're seeing something we don't expect. We're thinking, okay, maybe we need to account for the fact that the observations are not independent within clusters. And we can do that by looking at the distribution within each cluster. So you can see each cluster has a different kind of center of their distribution of test scores. So this indicates to us that potentially we need to account for the correlation within clusters, because what this suggests to us is that there may be a random intercept model that would be a better fit for the data, because each of these box plots has kind of a different center point. And then kind of in more detail, we can look at the association between weight and test score by clinic, and the clinics here are color coded. So you can see that for the different clinics have kind of a different joint distribution of weight and test score. Excuse me. So this is further indication that we may need to consider something like a mixed model. So I'm gonna, this something we could consider, but I'm not gonna, detail for the sake of time, is multiple regressions within each clinic, which is kind of dividing everything into these scatter plots, or treating clinic as a fixed effect, which makes certain assumptions, and again, is generally not the way to go for clustered data. And then finally, kind of the mixed effects model that we would like to emphasize here is specified by this additional random intercept component. And now we see that we no longer have a significant effect of weight on test score. Now this is more in line with our original hypothesis. And we also noticed that we have kind of a large variance of 340 compared for the random effect compared with the residual variance of 224. So if we compute our interclass correlation coefficient, or our ICC, we end up with a value of about 0.6. So 60% of the variability of our outcome is coming from that between cluster component. So that's quite a bit. And then again, I'm going to kind of you also might want to take into account the correlation between the observations within a provider, which is just going to add a little bit to the complexity of the model, but isn't really going to change our conclusions too much. And then finally, we want to take a look at why we no longer see that significant effect for weight on test score. And we can do that with these kinds of plots. So essentially what's happened is in that big scatter plot with all the clinics, there looked like there was a positive association between weight and test score because we're not accounting for that clustering. So when you do account for the clustering within clinic, and again, here we're also accounting for the clustering within provider, you can see that these individual regression lines kind of that are predicted from the mixed model are pretty flat. So within a clinic and provider potentially, you no longer have a positive association. That positive association between weight and test score really only arises because we neglected to account for the correlation within clinics. So that's I think I'm going to stop there, and if anybody has questions, I'm happy to entertain those.